Have you ever looked up at the night sky and felt that overwhelming sense of awe, gazing into an endless sea of stars and wondering what's truly out there? That feeling, that deep, almost primal curiosity, is something we've all shared, and it's the very same impulse that has driven humanity to explore, discover, and question the nature of reality itself. But what if I told you that the universe is far stranger, far more mysterious, and infinitely more wondrous than we could ever imagine? Every day, astronomers and physicists uncover new cosmic puzzles that challenge not just what we know, but how we think about existence. From invisible forces shaping galaxies to baffling anomalies that defy our understanding of physics, the expanding universe is filled with secrets waiting to be revealed. Today, we're setting off on a journey together, a voyage through 25 of the most captivating mysteries the cosmos has to offer. This isn't just a list of facts, it's an invitation to step into the unknown, to wander through realms where time bends, matter behaves in impossible ways, and the fabric of space itself seems to whisper questions we're only beginning to understand. We'll explore enigmas that have puzzled scientists for decades and discoveries so fresh they're reshaping our entire view of reality. Each mystery is a piece of a grand cosmic puzzle, one that connects us not only to the farthest reaches of space, but to the very core of our own humanity, our endless drive to seek answers. So settle in, open your mind, and get ready to see the universe in a whole new light. Whether you're a seasoned space enthusiast or someone who's simply curious about the wonders above, this journey is for you. We're about to dive into the unknown, where every discovery raises new questions and every answer leads us deeper into the magnificent, mysterious expanse of the cosmos. Let's begin. Our journey begins with perhaps the most profound shock to modern cosmology, the discovery that the universe isn't just expanding, it's accelerating. For decades, the prevailing image was one of a cosmic explosion slowly winding down. After the Big Bang, everything was flung outward, and while that expansion would continue, scientists believed the relentless pull of gravity would act as a cosmic brake, gradually slowing the entire process. It was a beautiful, intuitive idea, but the universe, it turns out, had a stunning surprise in store. This revelation came from a seemingly catastrophic event, the death of stars. Astronomers used Type 1, a supernova, which are thermonuclear explosions of white dwarf stars, as cosmic mile markers. These explosions have a very predictable brightness, allowing scientists to precisely measure their distance. By observing how these distant supernovae appeared dimmer than expected, two independent teams made the same astonishing conclusion in the late 1990s. The most distant stellar explosions were much farther away than any model of a slowing expansion could account for. The only possible explanation was that the expansion of space itself wasn't slowing down at all. Instead, it was speeding up. Some unknown repulsive force was overwhelming the collective gravity of all the matter in the cosmos, pushing galaxies apart at an ever-increasing rate. This mysterious force was dubbed dark energy, and it remains one of the greatest enigmas in all of physics. We cannot see it, we cannot detect it directly, but we can see its overwhelming effect on the universe's evolution. Its nature is a complete puzzle. Is it a manifestation of a cosmological constant, a form of energy inherent to the fabric of empty space itself, as Albert Einstein once proposed and then famously dismissed as his greatest blunder? Or does it point to something even more exotic, like a new dynamic field that permeates the cosmos, whose strength could change over time? The implications are staggering. If this acceleration continues unchecked, dark energy dictates a profoundly lonely and cold fate for the universe, a big freeze or heat death, where galaxies are pushed so far apart that the sky will eventually go dark and the universe will become a vast, expanding emptiness. But if dark energy is the force pushing the cosmos apart, then what is it that's holding it all together? This brings us to our second great mystery, a cosmic ghost that permeates every galaxy and binds the universe on the largest scales, dark matter. We've found that the stars at the outer edges of spiral galaxies are moving far too quickly. According to the laws of gravity, the speed of a star's orbit should decrease the farther it is from the galactic center, much like the outer planets in our solar system move more slowly around the Sun. But that's not what we observe. Instead, those distant stars are whipping around at velocities that should be impossible, speeds that should fling them out into the void. The only logical conclusion is that there is far more mass in the galaxy than we can see, an enormous, invisible halo of some unknown material whose gravity is the only thing keeping these stars from flying away. This hidden scaffolding doesn't just affect single galaxies. Its gravitational influence bends the very fabric of reality around massive clusters of galaxies. When we train our telescopes on these distant clusters, we see a phenomenon called gravitational lensing, where the light from objects far behind the cluster is distorted into faint arcs and rings. The amount of bending is so extreme that it reveals a truly staggering amount of mass that is completely invisible to our telescopes. This matter does not emit, absorb, or reflect any form of light or electromagnetic radiation. It simply doesn't interact with light at all. It's a substance that, for all intents and purposes, is completely transparent, and yet it makes up roughly 27% of the entire universe. So what could it possibly be? For decades, the leading candidate has been a hypothetical type of particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, slow-moving, and would only interact with normal matter through gravity and the weak nuclear force, making them nearly impossible to detect. To find them, physicists have built exquisitely sensitive detectors deep underground, in abandoned mines and beneath mountains shielded from cosmic rays. They wait in profound silence and cold for the once-in-a-lifetime tremor that might be a dark matter particle bumping into an atomic nucleus. Other experiments, like the Alpha Magnetic Spectrometer on the International Space Station, scan the heavens for the unique signals of dark matter particles annihilating each other in the void. Yet, despite this global effort, dark matter remains elusive. We see its gravitational shadow everywhere, but we have yet to lay a hand on it. Its nature is one of the most pressing questions in physics because without this invisible glue, the universe as we know it would not exist. It was the gravitational pull of dark matter that first gathered the primordial gas after the Big Bang, providing the seeds for the first stars and galaxies to form. It is the hidden architecture upon which the visible cosmos is built. Every galaxy, including our own Milky Way, is embedded within a vast, massive halo of this mysterious substance, a silent partner in the cosmic dance that dictates the fate of everything we see. Yet for all its influence, the origin of these cosmic magnetic fields is a profound mystery. We have a good understanding of how they can be amplified and maintained once they exist through a process called the dynamo effect. This is similar to how our own planet generates its magnetic field, with the motion of conductive material like molten iron in Earth's core converting kinetic energy into magnetic energy. On a galactic scale, the turbulent motion of ionized gas and plasma, stirred by the birth and death of stars, can stretch, twist, and amplify a weak magnetic seed into the powerful fields we observe today. The problem isn't the amplifier, it's finding the battery. Where did that initial primordial magnetic seed come from in the first place? The challenge is that any initial seed field must have been immeasurably tiny, a faint whisper of magnetism in the newborn universe. The dynamo theory requires something to get started. Without that initial push, the process can't begin. So what generated the very first magnetic fields? Scientists have proposed several ideas, but each comes with its own set of puzzles. Some theories suggest they were generated in the extremely hot, dense conditions just after the Big Bang, through exotic phase transitions in the early universe. Others propose they were forged in the violent eruptions of the first stars or around the supermassive black holes at the centers of early galaxies. Yet, all of these events seem to happen too late or produce fields that are too weak to explain the magnetic signatures we now see woven throughout the cosmos. This mystery is further deepened when we consider the incredible scale of these fields. They don't just stop at the edge of a galaxy, they thread through the vast, empty spaces between galaxy clusters. In these immense cosmic voids where the density of matter is 1,000,000 times lower than in a galaxy, we still detect the faint imprint of magnetism. How did magnetic fields grow to fill such enormous volumes of space? It's as if an invisible network, a cosmic web of magnetic force, was laid down at the very beginning of time and has been guiding the evolution of the universe ever since. Unraveling this origin story is crucial because it's intertwined with so many other cosmic processes. Magnetic fields play a vital role in channeling material during the collapse of gas clouds to form new stars. They act as powerful accelerators, whipping charged particles to nearly the speed of light to create the cosmic rays that constantly bombard our planet. They even influence how galaxies evolve, providing pressure and structure to the interstellar medium. Without magnetism, the universe would look and behave very differently. And if you think the mysteries of dark energy and dark matter are baffling, wait until we try to create a universe in a laboratory. This brings us to one of the most precise and yet most confounding puzzles in all of cosmology, a problem that arises from our very best calculations of how everything began. We call it the cosmological lithium problem, and it's a case where our foundational theory of the Big Bang is almost perfect except for one tiny, nagging detail that refuses to add up. To understand this, we need to rewind the clock almost to the very beginning. In the first few minutes after the Big Bang, the entire universe was an unimaginably dense, hot soup of fundamental particles. Protons and neutrons zipped through this primordial fog, occasionally colliding and sticking together to form the first atomic nuclei. This brief, explosive period is known as Big Bang nucleosynthesis, and it's the process responsible for forging the universe's first hydrogen, helium, and a tiny smattering of lithium. For the most part, our mathematical models of this event are a stunning success story. The predicted abundances of hydrogen and helium isotopes match almost perfectly with the oldest observations we can make. It's a powerful confirmation that we really do understand the basic physics of the universe's first few minutes. But then there's lithium. The calculations are very precise. They tell us exactly how much lithium-7, a specific isotope, should have been created during that frantic 3-minute forge. And when we look out into the oldest stars in the halo of our galaxy, stars that formed from nearly pure primordial gas, uncontaminated by later generations of element-building supernova, we should see that predicted amount. But we don't. The numbers are off by a factor of about 3. The oldest stars have only about a third of the lithium that our best models of the Big Bang say they should have. It's not a small error bar, it's a glaring discrepancy. It's as if a master clockmaker built a perfect timepiece where every gear turns in flawless harmony, except for one tiny screw that is somehow both too big and too small at the same time. So where did the lithium go, or was it never made in the expected amounts to begin with? Scientists have been chasing down solutions to this puzzle for decades, and the answers seem to lie in one of two places. The first possibility is that our understanding of the nuclear physics itself is incomplete. Could there be unknown particles or forces at play in the early universe that altered the reaction rates? Some theorists have proposed ideas involving exotic particles that would have been present, subtly changing the pathways along which nuclei formed. Others have wondered if our measurements of how certain nuclei interact with each other in labs here on Earth might have a hidden margin of error that becomes critical under the extreme conditions of the Big Bang. The second, and perhaps more likely, possibility points to the stars themselves. These ancient stellar relics we use as cosmic time capsules are not inert. They have interiors that mix and churn over billions of years. It's possible that the lithium in their outer atmospheres, which is what we observe, has been slowly dragged down into their hotter interiors and destroyed. Lithium is a fragile element. It breaks apart at the temperatures found inside most stars. If these old stars have physical processes that can transport surface material inward, they could be gradually consuming the very evidence we're trying to measure, effectively hiding the primordial lithium away from our telescopes. This cosmic accounting error forces us to question everything we think we know about those first few minutes. It's a reminder that even our most successful theories can have a missing piece, a subtle flaw that points to a deeper layer of reality waiting to be uncovered. But just when we think we have the early universe figured out, a ghost from that ancient era sends a chill down the spine of modern cosmology. This brings us to our fifth mystery, one with a name that sounds like it's straight out of a spy thriller, the axis of evil. It's a perplexing anomaly buried within the oldest light we can see, the cosmic microwave background, and it threatens to undermine one of our most cherished cosmological principles. To understand why this is so shocking, we have to appreciate the cosmic microwave background itself. This faint glow is the cooled remnant of the Big Bang's fireball, a snapshot of the universe when it was just 380,000 years old. It's the foundation upon which our entire modern understanding of the cosmos is built. When we map this radiation across the entire sky, we see a beautiful, speckled pattern of tiny temperature fluctuations, hot and cold spots. These are the seeds of all future structure, the tiny density variations that would, over billions of years, gravitationally collapse to form galaxies and clusters. According to our fundamental models, these fluctuations should be completely random. They should show no special direction, no preferred axis, no grand design. This idea is enshrined as the cosmological principle. The universe on a large scale is homogeneous and isotropic. It should look the same in every direction with no center and no edge. Yet, when scientists began analyzing the incredibly precise data from satellites like WMAP and Planck, they found something deeply unsettling. Certain large-scale patterns in the temperature fluctuations aren't random at all. They appear to be aligned. It's as if the hot and cold spots are subtly organized along a particular axis that runs through the universe, an alignment that has been dubbed the axis of evil. This isn't just a minor statistical fluke, it's a persistent signal that has survived intense scrutiny and more advanced data collection. It suggests that the universe might have a preferred direction, a fundamental lopsidedness that completely contradicts the cosmological principle. The potential implications of this are staggering. If the universe isn't the same in all directions on the largest scales, it could mean our foundational theory of cosmic inflation, the idea of a sudden, exponential expansion in the first fraction of a second, is incomplete or needs serious revision. Inflation was proposed specifically to explain why the universe appears so uniform. The axis of evil anomaly whispers that this uniformity might be an illusion, that the primordial universe might have had a structure or a preferred direction imprinted upon it from the very beginning. Some theorists have proposed wild explanations, suggesting our universe might have collided with another universe in the multiverse, leaving a bruise on the sky. Others wonder if it's a clue that the fabric of space-time itself is more complex than we thought, perhaps twisted on a scale we can barely comprehend. Of course, the most conservative explanation is that it's simply a trick of the data, an artifact of how we subtract the foreground glow of our own Milky Way galaxy, or an unlikely but possible statistical coincidence. But as the data gets better and the signal persists, this comfortable explanation becomes harder to accept. The axis of evil remains a profound embarrassment to our standard models, a quiet but persistent hint that our universe might not be the perfectly smooth, random cosmos we thought it was, but something with a hidden architecture we are only just beginning to perceive. Just when we think we have a handle on the universe's expansion, a new and deeply troubling discrepancy emerges, one that has split the cosmology community and hints at a potential revolution in physics. This is the Hubble tension, and it represents a direct conflict between two of the most reliable ways we have of measuring the universe's expansion rate, a value known as the Hubble constant. On one side, we have the local universe, our cosmic neighborhood. Here, astronomers use what's called the distance ladder. It's a step-by-step process that starts with precise parallax measurements from satellites to nail down the distances to nearby stars. From there, they use those stars to calibrate the next rung, Cepheid variables. These are a special type of star that pulsates with a regularity directly tied to its intrinsic brightness. By measuring its pulse rate, astronomers know its true brightness. Comparing that to how dim it appears from Earth gives a precise distance. The final step involves finding these Cepheids within galaxies that also host Type 1a supernova, those same stellar explosions we discussed with dark energy. Because these supernovae are also standard candles, the Cepheids calibrate their true brightness, allowing us to measure distances to galaxies far across the universe. By observing how fast these galaxies are receding from us, their redshift, and knowing their precise distance, we get a direct local measurement of the Hubble constant. This method is meticulous, cross-checked, and incredibly robust. On the other side, we look back to the very beginning, to the cosmic microwave background. The Planck satellite mapped this ancient light in exquisite detail, capturing the faint temperature variations that are the blueprints for all future cosmic structure. Using our well-tested model of the universe, including the amounts of dark matter, dark energy, and the physics of the Big Bang, scientists can run the cosmic film in reverse. The precise characteristics of those hot and cold spots tell us exactly how fast the universe must have been expanding to produce the patterns we see. This gives us a prediction, a measurement of the Hubble constant from the early universe that should perfectly match what we see locally today, but it doesn't. The two values are stubbornly, undeniably different. The local measurement from the distance ladder suggests a faster expansion rate, while the early universe measurement from the CMB suggests a slower one. The gap between them is not a small error that can be explained away by marginal uncertainties. It is a significant and growing discrepancy that has persisted despite years of improved observations and more refined analyses from both camps. This isn't just a minor academic debate. It's a crisis in cosmology because it suggests one of our most fundamental assumptions about the universe might be wrong. So what could be the cause? Scientists are exploring two broad possibilities. The first, and more mundane, is that there is an unaccounted for systematic error in one of the measurements. Perhaps our understanding of Cepheid variables is incomplete, or maybe there is some subtle bias in how we measure the distances to the most far-flung supernova. Teams are constantly refining their methods, using new data from the James Webb Space Telescope to peer past the dust that might be clouding the Cepheid measurements, but so far the tension refuses to fade. The second, and far more exciting possibility, is that this is real and points to new physics. Our standard cosmological model, known as lambda CDM, is incredibly successful, but the Hubble tension might be its first major crack. Perhaps dark energy is not a constant but is evolving over time, becoming stronger and accelerating the expansion more than our models allow. Or maybe dark matter has properties we haven't yet discovered, interacting with itself or with light in ways that subtly alter the evolution of the cosmos. Some theorists have even proposed exotic ideas, like the existence of a new type of relativistic particle in the early universe that would change how we interpret the CMB data. This isn't just a mathematical puzzle, it's a detective story playing out on the grandest possible scale. The Hubble tension forces us to question the very tools we use to understand reality. It's a reminder that the universe is under no obligation to make sense to us, and that the most exciting phrase in science isn't eureka, but that's funny. But this cosmic acceleration driven by dark energy doesn't just tell us about the universe's present, it holds the key to its ultimate fate. The destiny of everything, every galaxy, every star, every atom hinges on the true nature of this mysterious force. Will the cosmos end in a whisper, a scream, or a violent reversal? Our best theories paint several dramatic and vastly different final chapters. The most widely accepted model, based on our current observations, is known as the Big Freeze or heat death. In this scenario, dark energy behaves as a constant, unchanging force, much like Einstein's cosmological constant. The acceleration continues at a steady pace forever. In the short term, this means our local group of galaxies will remain gravitationally bound, eventually merging into one colossal galaxy. But beyond our island, the view will become increasingly lonely. Over the next 100 billion years, the acceleration will push all other galaxy clusters so far away that their light can no longer reach us. The universe beyond our immediate neighborhood will fade to black, leaving our descendants, if any remain, with the mistaken belief that their galaxy is all that exists. As eons turn into ages, stars will eventually consume all their fuel and wink out one by one. The universe will grow cold and dark, a vast, expanding near-empty void where occasional flashes of light from dying stellar embers become rarer and rarer until eventually nothing happens at all. It is a quiet, gradual, and profoundly lonely end. But what if dark energy isn't constant? What if it grows stronger over time? This possibility leads to a far more violent and dramatic demise, the Big Rip. In this model, the repulsive force of dark energy doesn't just push galaxies apart, it intensifies without limit. First, it would tear apart the gravitational bonds holding clusters of galaxies together. Then, as the force grows even stronger, it would rip apart individual galaxies. The escalation would be terrifyingly methodical. About 60 million years before the end, the extreme acceleration would tear our solar system apart, pulling planets from the sun's grasp. In the final months, it would shred stars and planets themselves. In the last minutes, atoms and nuclei would be torn apart, and finally, in the last unimaginable instant, the very fabric of spacetime itself would be ripped to shreds. The universe would cease to exist in any recognizable form. The timeline for this catastrophic end depends entirely on how fast dark energy strengthens, a value physicists call its equation of state. Current observations place tight constraints on this possibility, suggesting a big rip is unlikely, but it remains a haunting specter in our cosmic forecast. There is a third classic possibility, the Big Crunch. This was the favored ending before the discovery of dark energy, a vision of the universe collapsing back in on itself. In this scenario, the density of matter and energy in the cosmos would be sufficient for gravity to eventually overcome the expansion. The universe would slow to a stop and then begin rushing inward. Galaxies would start to blue shift as they hurtle back toward each other. The temperature of the cosmos would rise as everything is compressed into a smaller and smaller volume. The sky would glow hotter and hotter, eventually becoming an oven that vaporizes all planets and stars. The end result would be a mirror image of the Big Bang, a fiery collapse into a singularity of infinite density. For the Big Crunch to happen, dark energy would need to be something that weakens or reverses over time. Or perhaps the overall density of the universe is much higher than we think. While current evidence makes this the least likely of the three primary fates, some models of a cyclical universe incorporate it, suggesting a Big Crunch could simply be the prelude to another Big Bang, an eternal cycle of birth, death, and rebirth. These are not just abstract ideas, they are scientific hypotheses that we are actively testing. The key to distinguishing between them lies in precisely measuring the equation of state of dark energy, how its pressure relates to its energy density. Is it exactly constant, as in the Big Freeze, or is it dynamic, changing over time to bring about a rip or a crunch? This is the primary goal of next-generation observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope. By mapping billions of galaxies and observing thousands of distant supernovae, they will measure the expansion history of the universe with unprecedented precision, hoping to catch any subtle evolution in the strength of dark energy. The fate of everything depends on the outcome of this cosmic detective work. But even as we grapple with these grand questions about the universe's ultimate fate, there's a much more immediate and tangible mystery hiding in plain sight, one that involves the very stuff you and I are made of. We call it the missing baryons problem, and it's a cosmic case of misplaced ordinary matter. For all the talk of dark matter and dark energy, it's easy to forget that the atoms making up planets, stars, and life itself, what physicists call baryonic matter, are supposed to be a specific fraction of the universe. Our most precise measurements of the cosmic microwave background tell us exactly how much of this normal matter should have been created in the Big Bang. When we then add up all the ordinary matter, we can actually see all the stars, all the glowing gas in galaxies, all the dust. We come up dramatically short. We can only account for roughly half of what the models insist must be out there. It's as if a cosmic inventory has revealed that half of all the atoms in the universe have simply vanished without a trace. So where did it all go? The leading suspect isn't some exotic new particle, but rather a vast, diffuse web of incredibly hot gas. Theorists call this the warm-hot intergalactic medium, or WIM. Picture the universe's large-scale structure not just as galaxies and clusters, but as an immense cosmic web of dark matter filaments. Along these invisible threads, ordinary matter is believed to be gathered into enormous, faint filaments of million-degree gas, stretching between galaxies and connecting clusters in a tenuous, steaming network. This gas is so hot it doesn't emit visible light, and so thin that it's nearly transparent, making it incredibly difficult to detect with conventional telescopes. Finding this hidden reservoir has become a major observational quest. Astronomers have turned to powerful X-ray and ultraviolet space telescopes like Chandra and XMM Newton to hunt for the faint signatures of this superheated gas. The strategy is ingenious. They look not at the filaments directly, but at the light from incredibly bright, distant objects called quasars. As this brilliant light journeys across the universe towards us, it passes through these invisible filaments of the WIM. The specific elements within the hot gas, like highly ionized oxygen and neon, absorb very particular wavelengths of this background light. By analyzing the quasar's spectrum, scientists can find these distinct telltale dips and fingerprint the presence of the hidden matter. It's like using a distant lighthouse to illuminate the fog around it. Other methods involve looking for the faint, diffuse X-ray glow that this hot gas might emit, or even studying the subtle ways it distorts the cosmic microwave background. Slowly, piece by piece, the evidence is mounting. Recent observations have begun to confidently detect these massive filaments, finding the predicted amounts of oxygen and other elements exactly where the models said the missing matter should be hiding. It appears the mystery is close to being solved, not with a revolutionary new physics, but with a sophisticated game of cosmic hide and seek. Why does finding these missing atoms matter so much? It's the final piece of the ordinary matter puzzle. Confirming that the WIM holds the universe's missing baryons would complete our census of the content of the cosmos, validating our understanding of the Big Bang and the formation of cosmic structure. It assures us that we fundamentally understand the behavior and whereabouts of the familiar atoms that build everything we can see and touch, allowing us to focus with even greater confidence on the deeper enigmas of the dark universe that still lie beyond our grasp. While we search for the universe's missing atoms, another invisible rain is constantly bombarding our planet, carrying energies so immense they defy our understanding of physics itself. These are ultra-high-energy cosmic rays, and they are the most energetic particles ever observed in nature. We're not talking about a slight advantage over our best machines. A single one of these subatomic projectiles can carry the kinetic energy of a professionally thrown baseball, all compressed into a particle smaller than an atom. That is a level of energy millions of times greater than what the Large Hadron Collider can produce. Their existence is a monumental puzzle because something, somewhere in the universe, is acting as a natural particle accelerator of almost unimaginable power. Detecting these cosmic bullets is a challenge precisely because they are so rare. At the very highest energies, fewer than 1 particle per century lands on a square kilometer of Earth. You can't just point a telescope at the sky to find them. Instead, scientists have built enormous observatories that turn entire landscapes into detectors. The Pierre Auger Observatory in Argentina, for instance, covers 3,000 square kilometers, an area the size of Rhode Island with 1,600 water tanks spaced over a mile apart. When an ultra-high-energy cosmic ray slams into the top of our atmosphere, it doesn't reach the ground. Instead, it creates a massive cascade of secondary particles, an avalanche of matter and energy that spreads out for kilometers in what's called an extensive air shower. These particles hit the water in the tanks, creating faint flashes of light called Cherenkov radiation that allows scientists to reconstruct the original particle's energy and direction. Other observatories, like the Telescope Array in Utah, use specialized telescopes to observe the faint ultraviolet fluorescence light that the air shower itself emits as it streaks through the atmosphere. It's a form of astronomical detective work, studying the aftermath of a spectacular collision to understand the bullet that caused it. But even with these massive detectors, pinpointing the source is incredibly difficult. That's because these particles are not photons of light. They are charged primarily protons or atomic nuclei. As they travel across millions of light years, they are deflected by the weak but pervasive magnetic fields that fill interstellar and intergalactic space. Their paths are scrambled, making it nearly impossible to trace them back in a straight line to their origin. It's like trying to find the source of a river by following a single leaf that has been tossed and turned by countless currents and eddies along the way. Despite this, large statistical studies have begun to hint at possible origins. There appears to be a correlation between the arrival directions of the highest energy events and the locations of active galactic nuclei, incredibly powerful engines powered by supermassive black holes actively feeding on surrounding material. These monstrous objects can shoot out jets of plasma and particles at nearly the speed of light, making them prime suspects for these natural accelerators. Other potential sources include even more extreme events like gamma-ray bursts or the violent mergers of neutron stars. Yet, the very existence of these particles presents a profound theoretical challenge known as the Greisen-Zatseping-Kuzmin limit or the GZK cutoff. This isn't a limit of our detectors, it's a fundamental speed limit imposed by the fabric of the universe itself. Space is not completely empty. It is filled with the dim afterglow of the Big Bang, the cosmic microwave background radiation, a sea of low-energy photons. For a proton traveling from a distant galaxy at near the speed of light, this cosmic background is not a faint whisper, it's a dense fog. According to physics, a proton with energy above this GZK limit should interact with these background photons within a relatively short distance, losing a significant amount of its energy long before it could ever reach Earth. The limit calculates that no proton should be able to reach us from a source farther than about 160 million light-years away. This creates a cosmic horizon, a sphere beyond which we should see nothing. The mystery is that we do detect particles with energies far beyond this theoretical limit. This means one of two incredible things must be true. Either these particles are coming from something relatively close by within our local cosmic neighborhood, within that 160 million light-year horizon, which makes their incredible energy even harder to explain because the source has less distance to accelerate them. Or our understanding of high-energy particle physics is incomplete. Perhaps there is new physics beyond the standard model that allows these particles to travel farther than we think. Or maybe they are not protons at all, but a more exotic form of matter that doesn't interact as strongly with the background radiation. Each ultra-high-energy cosmic ray that breaks the GZK limit is a messenger from the extremes of the universe, carrying not just immense energy, but the potential to rewrite the laws of physics as we know them. As our own Milky Way galaxy journeys through the cosmos, it isn't drifting aimlessly. We are moving at a staggering velocity of over 600 kilometers per second, pulled by a relentless gravitational force toward a specific point in the sky, a region in the constellation Centaurus. For decades, the source of this immense pull was one of astronomy's most perplexing enigmas, a mystery we aptly named the Great Attractor. The challenge in solving it was profound, because the center of this gravitational pull lies directly behind the plane of our own galaxy, a zone obscured by thick clouds of gas and dust that block our visible light view. It was like trying to find a mountain range hidden behind a permanent, impenetrable fog. The breakthrough came not from optical telescopes, but from new eyes that could see through the cosmic dust. Sky surveys that mapped the universe in infrared light, like the 2-micron all-sky survey, and radio telescopes that could detect the hydrogen gas in distant galaxies, began to pierce the veil. They revealed that the Great Attractor wasn't a single, monstrous object. Instead, it is the colossal gravitational core of our local supercluster of galaxies, a structure known as Laniakea, which means immense heaven in Hawaiian. This vast cosmic continent is centered on an enormously dense cluster of galaxies called the Norma Cluster, which acts as the gravitational anchor for 100,000 other galaxies, including our own Milky Way. The pull we feel is the collective gravity of this entire immense structure, a fundamental force shaping the motion of our local universe. But the story of our motion is not just about what's pulling us, it's equally about what's pushing us. Astronomers discovered that the Great Attractor alone could not account for the full velocity of our local galactic flow. There had to be another factor, a repulsive force contributing to our journey. This led to the discovery of an equally fascinating counterpart, the dipole repeller. Unlike the dense concentration of the Great Attractor, the repeller is a vast, underdense region of space, a cosmic void. In the grand tug-of-war of gravity, an area with far less matter than the cosmic average creates a kind of gravitational deficit. While it doesn't actively push matter away, it exerts an influence by not pulling as strongly as the surrounding regions. Imagine being in a boat on a river. You're pulled toward a powerful downstream current, but you're also pushed from behind because the water level behind you is lower. The dipole repeller is that low-pressure region, a void in the direction of the constellation Pisces, whose relative emptiness allows the pull from the opposite direction to dominate more effectively. Mapping this intricate cosmic dance required building detailed three-dimensional charts of the universe's large-scale structure. Projects like the Cosmic Flows Survey have meticulously measured the distances and velocities of thousands of galaxies. By plotting their positions and motions, scientists can create a flow field map, tracing the paths of galaxies as they stream along gravitational gradients. These maps reveal the grand confluence of cosmic structure, showing how galaxies flow along invisible rivers of dark matter toward immense clusters and away from empty voids. Our journey toward the Great Attractor is just one part of this vast universal traffic pattern, a single current in a network that spans hundreds of millions of light years. Understanding this dynamic interplay between the attractor and the repeller completes our picture of local cosmic motion. It illustrates a fundamental principle of cosmology. Gravity is a dual-faced force. It pulls us toward overdense regions of mass and effectively pushes us from underdense regions. This gravitational landscape, shaped by the invisible hand of dark matter, dictates the paths of galaxies and charts the future of our local universe. As we continue to refine these maps with ever more powerful telescopes, we not only solve the mystery of our own galaxy's motion, but also gain a deeper appreciation for the delicate and powerful forces that sculpt the cosmos on the grandest of scales. But just as we map the grand structure pulling our galaxy, we encounter a paradox that strikes at the very heart of physics, a puzzle so deep it questions our understanding of reality itself. This is the black hole information paradox, and it begins with a seemingly simple question with devastating implications. What happens to the information about an object when it falls into a black hole? According to Einstein's general relativity, the answer is simple: it's gone. The object is crushed into the singularity, and all the unique details that described it, what it was made of, its shape, its quantum state, are irretrievably lost behind the event horizon, the point of no return. The only things a black hole reveals about itself to the outside universe are its mass, its electric charge, and its spin. This idea is sometimes called the no-hair theorem, implying black holes are the ultimate simpletons, balding giants that remember almost nothing of what they consume. The problem is that this complete loss of information violently contradicts a fundamental tenet of quantum mechanics, the principle of unitarity. In the quantum world, information is never truly lost. It can be scrambled, diffused, and transformed into an incredibly complex form, but it must, in principle, be recoverable. The universe, according to quantum physics, is fundamentally predictable. If you know the complete quantum state of a universe at one time, you should be able to calculate its state at any point in the past or future. If black holes permanently erase information, they create a fundamental unpredictability, a tear in the fabric of quantum law. For decades, physicists assumed this was just a strange quirk, that the overwhelming gravity of a black hole somehow provided an exception to the quantum rules. That was until Stephen Hawking made a stunning calculation that turned this peculiarity into a full-blown crisis. Hawking showed that black holes aren't completely black. Due to quantum fluctuations near the event horizon, they slowly emit radiation and lose mass, a process we now call Hawking radiation. This radiation is thermal, it's random heat. It contains no information whatsoever about what fell into the black hole. Over unimaginable eons, a black hole will radiate away all of its mass and evaporate completely. And therein lies the paradox. If the black hole vanishes and all that's left is this random thermal radiation, then the information about everything it ever consumed is gone forever. The universe's quantum ledger has been irrevocably erased. This conclusion was so unsettling that Hawking himself declared it meant that even our past was not predictable, a notion that undermines all of physics. This clash between the smooth spacetime of general relativity and the strict information preservation of quantum mechanics became known as the black hole information paradox. For years, physicists tried to find a way out. Perhaps the information is somehow encoded in the Hawking radiation, but in such a subtle, scrambled way that we simply don't know how to decode it yet. This is like saying burning an encyclopedia doesn't destroy the information because the specific pattern of smoke particles and ashes could, in theory, be used to reconstruct every word, a notion that seems practically impossible. The debate intensified, leading to an even more bizarre proposal, the firewall paradox. If information is to escape a black hole via radiation, it requires a drastic mechanism. Some physicists argued that to break the entanglement between particles inside and outside the hole, the event horizon would have to be a seething wall of incredibly high-energy particles, a firewall that would instantly incinerate any astronaut falling in. This solved the information problem but created a new one, as Einstein's theory insists that crossing the event horizon should be an uneventful experience for the falling observer. You can't have both. Either general relativity is wrong at the horizon, or quantum mechanics is wrong about information. The most promising resolution to this decades-long crisis comes from a revolutionary idea called holography. The holographic principle suggests that all the information describing a three-dimensional volume of space, like the interior of a black hole, can actually be encoded on its two-dimensional boundary, the event horizon. Think of it like a hologram on your credit card, a two-dimensional surface that encodes all the information needed to project a three-dimensional image. In this view, when an object falls into a black hole, it doesn't actually pass through the horizon and vanish. Instead, its information is smeared out and stored on the surface of the horizon like a cosmic fingerprint. Then, as the black hole evaporates via Hawking radiation, this information on the surface is slowly and subtly imprinted onto the outgoing radiation particles. The information was never truly lost. It was just translated into a radically different language and emitted back into the universe over eons. Recent advances in string theory and gravitational physics have provided tantalizing evidence for this holographic idea. Calculations in certain simplified model universes have shown that the process of black hole evaporation can indeed be unitary, preserving information. The key is that the information isn't carried out by individual particles of radiation, but by incredibly complex correlations between them. It's the difference between trying to send a message by throwing individual letters one by one into the wind versus carefully printing them on a piece of paper. The letters are the same, but the information is in the arrangement. While the holographic principle is not yet proven, it offers a breathtakingly elegant solution, suggesting that our perception of a three-dimensional reality might be a projection from a deeper, two-dimensional law written on the boundaries of our cosmic horizon. Solving the information paradox may not just tell us what happens to stuff that falls into black holes. It may reveal that the universe itself is the most complex hologram of all. Just when we think we've encountered every extreme the universe has to offer, it delivers a signal so powerful and so brief it defies belief, a flash of radio energy that outshines an entire galaxy for a mere thousandth of a second, then vanishes without a trace. These are fast radio bursts, or FRB, and they are one of the most electrifying puzzles in modern astronomy. Imagine the entire energy output of our Sun over 80 years, unleashed in less time than it takes to blink. Now imagine that this titanic flash comes from halfway across the universe, and we have no idea what could possibly create it. That is the essence of an FRB, a cosmic scream in the dark, a message written in radio waves that we are only just beginning to decode. The story of FRBs began in 2007, when astronomer Duncan Lorimer was sifting through archived data from the Parkes Radio Telescope in Australia. He found a single, spectacular spike of radio energy that had been recorded 6 years earlier, a burst so intense it sat well above the background noise, but so short it had been initially dismissed as terrestrial interference. This one-off event, now known as the Lorimer burst, sparked a new field of astronomy. For years it stood alone, a cosmic oddity that some scientists even doubted was real. But then more were found. Today, we've detected hundreds of these events, and with each new detection, the mystery has only deepened. We now know FRBs come in two distinct flavors, repeaters and one-offs. Some sources, like the famous FRB 1211-2, fire off bursts over and over again in seemingly random patterns. Others blast just once and are never heard from again, suggesting their origin might involve a catastrophic, universe-shattering event. Locating the source of these bursts has been a monumental challenge. Because they last only milliseconds, pinpointing their origin requires a telescope that can not only see a huge portion of the sky at once, but also process data at an incredible speed. The breakthrough came with the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. This revolutionary telescope, which looks like a series of half-pipes from a snowboard course, has no moving parts. Instead, it uses digital signal processing to stare at a massive strip of sky every day, making it an FRB hunting machine. Thanks to CHIME and other powerful arrays, we've now localized many bursts to their host galaxies, often billions of light-years away. This in itself was a revelation confirming that these are indeed extragalactic events, originating from far beyond our Milky Way. So what cosmic engine could possibly power such a brief, yet unimaginably energetic flash? The prime suspect for at least some of these bursts, especially the repeaters, is a type of neutron star called a magnetar. Neutron stars are already the densest, most magnetic objects in the universe, the crushed cores of massive stars that went supernova. A magnetar is a neutron star on steroids with a magnetic field 1,000 trillion times stronger than Earth's. These fields are so intense they literally twist the star's crust. Imagine the magnetic field building up unimaginable stress until the crust suddenly snaps like a tectonic earthquake, releasing a vast amount of energy in a starquake that shakes the magnetar to its core. This catastrophic event could eject a massive blast of radio waves, a perfect model for a fast radio burst. In 2020, this theory received stunning support when a magnetar within our own galaxy, known as SGR 1935+215, erupted with a radio burst that looked and sounded exactly like the faint, closer-by versions of the cosmological FRBs we'd been seeing from distant galaxies. It was a smoking gun, proving that at least one type of object is capable of such a feat. But the magnetar theory doesn't explain everything. The most distant FRBs are so incredibly energetic that it strains the limits of what even a magnetar might be capable of producing. This has led astronomers to propose more exotic and violent origins. Could some FRBs be the birth cry of a new black hole, or the collision of two ultra-dense objects like neutron stars? Perhaps they are the result of cosmic strings, theoretical defects in the fabric of spacetime vibrating like plucked guitar strings. For the one-off bursts, a cataclysmic event like a black hole devouring a neutron star could provide the necessary energy, obliterating the source in the process and explaining why we never hear from it again. The true value of FRBs, however, may extend far beyond merely figuring out what causes them. These signals are not just flashes, they are cosmic journeys. As they travel across millions or billions of light years, their radio waves pass through clouds of ionized gas, the tenuous material that floats in the space between galaxies. Different radio frequencies travel at slightly different speeds through this material, causing the burst to disperse. The higher frequencies arrive at our telescopes just a fraction of a second before the lower ones. By measuring this smear, astronomers can calculate the total amount of material the signal has passed through. This turns every FRB into a powerful tool for weighing the universe's missing matter, that very same whim we went searching for with other methods. Each localized burst gives us a single, precise measurement along one specific line of sight, and by collecting enough of them, we can begin to map out the distribution of this elusive intergalactic plasma in 3 dimensions, charting the cosmic web itself. We are now in a golden age of discovery for these events. With every new burst detected and localized, we gather more clues. The race is on to find an FRB source in a type of galaxy we haven't seen before, or to catch one in the act with other telescopes that can see in gamma rays, X-rays, or optical light. A multi-messenger view of an FRB could instantly crack the case wide open, telling us precisely what occurred in that distant galaxy during that fleeting millisecond. These mysterious pulses are more than just a cosmic curiosity. They are both a message and a messenger. They carry within their brief signal the signature of their violent birth and a detailed diary of their long journey through the cosmos, offering us a chance to solve 2 profound mysteries at once: the nature of the most energetic events in the universe and the architecture of the invisible matter that fills it. And just as we tune our ears to the brief, energetic crackles of fast radio bursts, we also listen for a very different kind of signal, one that is steady, narrow, and deliberate. This is the dream of SETI, the search for extraterrestrial intelligence, a decades-long endeavor to find a message among the stars. While we've yet to receive a confirmed greeting, one event from the summer of 1977 stands out as the most tantalizing maybe in the history of the search, a mystery known simply as the WOW signal. It was August 15th, and volunteer Jerry Amon was poring over reams of printed data from Ohio State University's Big Ear radio telescope. The telescope was methodically scanning the sky, and its computer printed out strings of alphanumeric characters representing signal strength. For the most part, the printouts were a sea of noise, empty space, and the faint hiss of natural cosmic objects. But then, Amon's eye caught something extraordinary, a sequence of characters so powerful it leapt off the page, 6EQUJ5. In the system the computer used, this meant a signal had registered at an intensity 30 times louder than the background noise of deep space. It was a narrowband radio signal precisely at the frequency of 1420 MHz, the emission line of neutral hydrogen. This is significant because hydrogen is the most common element in the universe, and many scientists, including SETI pioneer Philip Morrison, had suggested it would be a natural, universal channel for any civilization wishing to announce its presence. Stunned, Jerry Amon circled the sequence of characters and wrote beside it a single, now famous word of astonished commentary: "Wow." The signal had all the hallmarks of an artificial, extraterrestrial broadcast. It was incredibly strong, extremely narrow in bandwidth, and it appeared and then disappeared exactly as expected for a signal from a fixed point in space as the Earth rotation swept the telescope's field of view across it. It lasted for a full 72 seconds, the maximum window the Big Ear could observe any single point, and then it was gone, despite numerous attempts over the years to find it again using more powerful telescopes like the Very Large Array, the WOW signal has never been Chinese letter. Its one-time only nature is the core of its mystery. If it was aliens, why would they transmit just once? The most likely natural explanations have also fallen short. It couldn't have been a satellite or a plane, as they move and would have caused a Doppler shift in the frequency, which wasn't observed. It was not a reflection of a terrestrial signal bouncing off space debris, as that would have been traceable. For over 4 decades, the WOW signal has remained an enigmatic blip, a one-off event that perfectly matched what we thought we were looking for, yet forever just out of reach for confirmation. The search, however, has evolved dramatically since then. SETI is no longer just about listening for a deliberate hello. It's about scanning the cosmos for any sign of technology or technosignatures. This broadens the hunt beyond narrowband radio signals to include laser pulses, the spectral signs of industrial pollution in a distant exoplanet's atmosphere, the unnatural heat signature of a Dyson sphere megastructure enveloping a star, or even the city lights of an advanced civilization on the night side of a planet. Modern initiatives are using some of the world's most powerful telescopes to conduct these surveys. The Breakthrough Listen project, for instance, is using the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia to scan 1 million nearby stars and the 100 galaxies closest to us, generating more data in a day than the entire SETI effort did in its first 50 years. They use sophisticated algorithms to sift through this immense ocean of data, looking for that one needle of a signal that doesn't fit the natural pattern. Yet, for all our technological advancement, the fundamental challenge remains the same: distinguishing a true signal from the countless sources of interference our own civilization creates. Every microwave oven, every satellite, and every radio station broadcasts a signal that can sometimes trick our sensitive equipment. SETI scientists must be the ultimate skeptics, applying rigorous filters to dismiss these false positives. The goal is to find a signal that is not just artificial, but unambiguously extraterrestrial, one that can be verified by multiple telescopes across the world. The WOW signal, for all its intrigue, never achieved that level of confirmation, which is why it remains in the category of a fascinating anomaly rather than a discovery. The implications of a confirmed detection are, of course, world-altering. It would answer one of humanity's oldest questions, are we alone? But perhaps more importantly, it would provide a cosmic context for our own existence. Knowing that another intelligence has also navigated the challenges of evolution, technology, and survival would suggest that the universe is, in fact, teeming with life and potential. It would offer a profound sense of connection across the vast interstellar distances, a reminder that the same laws of physics and chemistry that shaped us here on Earth have given rise to another thinking, technological species somewhere else. The silence we perceive may not be an empty void, but simply a matter of scale and time. We may just need to listen longer and in more ways to finally hear the conversation that has already begun. For years, scientists were utterly baffled. No known force of gravity or friction could account for this tiny, relentless tug. The anomaly was so persistent and so consistent that it sparked a tantalizing, and for some, a thrilling possibility. Were we seeing the first hint of a failure in Einstein's theory of general relativity? Could there be some new, unknown physics at play, a subtle modification to the laws of gravity that only became apparent in the vast, quiet expanse of the outer solar system? The pioneer anomaly became a beacon for theoretical physicists who proposed a host of exotic explanations, from the existence of unseen dark matter in our solar system to the influence of higher dimensions or even the subtle drag of a cosmic ether. It was a classic scientific mystery, a tiny deviation with the potential to unravel our entire understanding of the cosmos. The quest to solve it became a painstaking forensic investigation, a decades-long effort that involved recovering old telemetry data from vintage magnetic tapes and computer printouts, and building incredibly sophisticated computer models of the spacecraft themselves. The turning point came when scientists realized they had to think not like astrophysicists but like engineers. The culprit, it turned out, wasn't a force from the outside but a gentle push from within. The Pioneer probes were powered by plutonium-filled radioisotope thermoelectric generators, and these units generated a tremendous amount of heat. The spacecraft were also designed with a specific orientation. Their main dish antennas were always pointed directly at Earth to communicate. This meant that the heat generated by the onboard electronics and the power source was radiating away from the craft, but not perfectly evenly. A slightly larger fraction of this thermal radiation was emitted from the back of the dish, the side facing the main body of the spacecraft. According to the simple law of conservation of momentum, every photon of heat carrying energy away from the spacecraft also imparts a minuscule amount of thrust in the opposite direction. This is the principle behind photon rockets, albeit on an almost imperceptible scale. For Pioneer, this resulted in a very slight but continuous push back toward the Sun, an effect that perfectly matched the anomalous deceleration. The mystery was solved not by discovering new physics, but by accounting for an old, well-understood effect with exquisite precision. While the solution may have been more mundane than some had hoped, the legacy of the Pioneer anomaly is anything but. It taught us an invaluable lesson in humility and the incredible importance of meticulous accounting. It forced scientists to consider every conceivable variable when calculating the trajectories of deep space missions, leading to a new level of precision in navigation. This rigorous approach is now standard practice for missions like New Horizons as it flew past Pluto and the Voyager probes as they journey into interstellar space. The anomaly also served as a powerful catalyst for developing new tools and techniques to test the fundamental laws of gravity with even greater accuracy. It inspired a renewed focus on tracking other spacecraft, like the Cassini mission to Saturn, to see if they exhibited similar behavior, effectively using the solar system as a grand laboratory for physics. In the end, the Pioneer anomaly stands as a brilliant testament to the scientific process, an intriguing puzzle that pushed the boundaries of investigation, leading not to a revolution in physics, but to a deeper, more thorough understanding of the complex and beautiful engineering we send out to explore the stars. But as we map the grand flows of galaxies and the vast cosmic web, we're forced to confront a startling possibility about our own cosmic address. What if our place in the universe isn't average or typical? What if, instead of being in a perfectly uniform cosmos, we're actually residing inside a gigantic cosmic void? This idea is known as the KBC void, named after the astronomers Keenan, Barger, and Cowie, and it presents a direct challenge to the foundational cosmological principle. For centuries, a core assumption in cosmology has been that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction with no special place or center. The KBC void hypothesis suggests we might be the exception to that rule. Evidence for this local underdensity comes from painstakingly counting galaxies and measuring their distances. When astronomers create three-dimensional maps of our cosmic neighborhood, they find that the density of galaxies and galaxy clusters increases the farther out we look. Immediately around us, out to a distance of about 1 billion light-years, space is significantly emptier than the cosmic average. We appear to be sitting in a spherical region of relative nothingness, a vast bubble of lower density that spans a staggering 1 to 2 billion light-years across. To put that immense scale into perspective, our entire local group of galaxies, including the Milky Way and Andromeda, is only about 10 million light-years wide. This void is 100 times larger, a true cosmic cavern. This isn't just about a feeling of emptiness, it has measurable physical consequences, particularly for the Hubble tension we discussed earlier. The expansion rate of the universe isn't perfectly uniform everywhere. In a region with less matter, like a void, the gravitational pull holding things together is weaker. This means that space inside the void can expand a bit faster than the global average. If we are indeed inside this local underdensity, our measurements of the Hubble constant using nearby supernova and Cepheid variables would naturally give a slightly higher value because we're measuring a locally faster expansion rate. Meanwhile, the measurement from the cosmic microwave background gives the true, global average expansion rate from the early universe. The KBC void could therefore provide an elegant solution to the Hubble tension, explaining the discrepancy not with new physics, but simply with our unlucky location in a slightly emptier part of the cosmos. Not all cosmologists are convinced, however. The debate hinges on the precise scale of galaxy surveys and the methods used to define an average density. Critics of the void hypothesis argue that while local underdensities exist, the proposed size of the KBC void is so enormous that it itself would violate the cosmological principle it seeks to challenge. Finding a void that large is statistically very unlikely in our standard model of the universe. Proponents counter that our telescopes may still be underestimating the true number of faint, dwarf galaxies in our local volume, which could make the void appear emptier than it truly is. Others are conducting ever larger galaxy redshift surveys to definitively map the boundaries of this proposed structure and see if it holds up. The resolution of this debate will profoundly shape our cosmic perspective. It either reinforces the idea that we live in a perfectly average place in the universe, or it tells us that our home is a rare and unusual quiet zone, a cosmic backwater whose unique properties have been subtly influencing our measurements of the entire cosmos all along. Even as we grapple with the possibility of living in a vast cosmic void, another profound mystery emerges from the depths of space, one that seems to challenge our understanding of the universe's very structure on the largest scales imaginable. This mystery involves some of the most luminous objects in the cosmos, quasars, and a peculiar property of their light that has no business being coordinated across billions of light-years. It's the strange case of the aligned quasar polarization axes, a finding so unexpected that it hints at a cosmic architecture we have yet to fully comprehend. To understand why this is so baffling, we first need to understand what a quasar is and what polarization means. A quasar, or quasi-stellar object, is the incredibly bright core of a distant galaxy, powered by a supermassive black hole that is actively feeding on surrounding gas and dust. As this material spirals into the black hole at nearly the speed of light, it forms an intensely hot accretion disk and often shoots out powerful jets of radiation and particles. This makes quasars the most brilliant beacons in the universe, visible from staggering distances. Now, light is an electromagnetic wave, and normally, these waves vibrate in all different directions as they travel through space. Polarization is the process of filtering that light so its waves oscillate in a single, preferred direction. Think of it like sunlight reflecting off the surface of a lake. The glare becomes polarized, which is why polarized sunglasses can block it out, allowing only light vibrating in a specific orientation to pass through. In astronomy, studying the polarization of light from distant objects can tell us about magnetic fields, the composition of dust, and the geometry of the object emitting the light. The mystery began when astronomers started to study the polarization of light from quasars spread across vast swaths of the sky. According to the foundational cosmological principle, which states that the universe should be uniform and have no preferred direction on large scales, the polarization directions of these quasars should be completely random. There is no reason why the light from a quasar in the northern part of the sky should have its polarization angle aligned with that of a quasar in the southern sky, billions of light years away. They are causally disconnected, they have never been in contact with each other, and there is no known physical mechanism that could possibly coordinate their behavior across such unimaginable distances. Yet, that is precisely what some studies have suggested. When researchers compiled data from hundreds of quasars, they found a startling statistical correlation. Their polarization axes were not randomly oriented. Instead, they showed a surprising degree of alignment over billions of light years, pointing in a similar direction across the cosmos. This is not a small-scale local effect. It is a large-scale cosmic anisotropy, a preferred direction in the universe that, if confirmed, would force us to rewrite the textbooks. The initial evidence for this alignment was met with intense skepticism, as any challenge to the cosmological principle should be. The first and most obvious question was whether this was a real physical phenomenon or merely a systematic error in the observations or the data analysis. Could it be an effect introduced by our own instruments, or perhaps by interstellar dust within our own Milky Way galaxy that is polarizing the light in a consistent way before we even see it? Teams have worked tirelessly to rule out these local contaminants, and while some early claims of alignment have been moderated by more precise data, a curious signal persists, particularly for quasars that are very far apart but whose polarization vectors seem to point in a coordinated way. If this alignment is indeed real and not an artifact, the implications are staggering. It would suggest that the universe has a fundamental handedness, a large-scale structure, or a preferred axis that was imprinted at the very moment of creation. Some theorists have proposed that this could be a signature of primordial magnetic fields that permeated the entire universe in its infancy, fields so vast and organized that they could influence the alignment of galactic structures across cosmic time. Others have wondered if it points to something even more exotic, like the influence of a unique, never-before-detected field that interacts with light across the cosmos, or perhaps even evidence that the universe is not isotropic but has a subtle spin or rotation on the largest scales, an idea that would turn modern cosmology on its head. The quest to solve this mystery is driving the development of new and more precise polarization surveys. Instruments like the upcoming Light-Bird space mission and advanced ground-based observatories are designed to measure the polarization of cosmic light with unprecedented accuracy, not just from quasars but from the cosmic microwave background itself. They will be looking for any whisper of a preferred direction, any hint of a grand cosmic design that we have so far overlooked. Whether the final answer lies in new physics or in a deeper understanding of systematic errors, the investigation itself pushes the boundaries of how we see the universe. It forces us to question one of our most fundamental assumptions and reminds us that the cosmos may still hold grand, coordinated patterns waiting to be decoded, patterns that could reveal the deepest secrets of how everything began. Yet this cosmic speed limit is not just a theoretical curiosity. It presents a direct and profound challenge to our observations. The mystery is that we routinely detect cosmic rays with energies that shatter this GZK cutoff, particles arriving at Earth with energies that, according to our best physics, should have been sapped away long ago if they traveled from a distant source. This creates a fascinating paradox. Either these ultra-high energy particles are coming from relatively nearby sources within our local cosmic neighborhood, within that 160 million light-year horizon, which makes their incredible energy even more difficult to explain, as a local source has less distance to accelerate them to such phenomenal speeds. Or our understanding of high-energy particle physics is incomplete, and these messengers are revealing new laws of nature that operate at energies far beyond what we can create in our terrestrial colliders. To untangle this puzzle, scientists have built some of the most vast and unconventional observatories on Earth. Facilities like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah don't look like traditional telescopes at all. They are sprawling networks of detectors that cover hundreds of square kilometers because catching these rare particles requires casting an enormous net. The telescope array, for instance, consists of over 500 scintillator surface detectors spread across a desert area nearly the size of New York City, paired with fluorescence telescopes that gaze at the night sky. When an ultra-high-energy cosmic ray strikes the atmosphere, it creates a massive cascade of secondary particles, an extensive air shower that rains down over a wide area. The surface detectors record the arrival time and intensity of this particle shower, while the telescopes capture the faint ultraviolet glow it produces as it streaks through the air. By combining these signals, physicists can reconstruct the energy, direction, and identity of the primary particle with remarkable precision. The data from these experiments paints a complex picture. When they plot the number of cosmic rays detected against their energy, they see a spectrum that mostly follows the expected pattern. The number of particles drops off drastically as the energy increases. And then, right at the predicted GZK cutoff energy, there is a noticeable suppression, a steep drop in the number of events. This is a tremendous victory for fundamental physics, confirming that the interaction with the cosmic microwave background is real and doing exactly what theorists said it would. But the plot doesn't end there. The graph doesn't simply fall to zero. A few stubborn events defiantly appear beyond the cutoff, their energies soaring into a realm that should be forbidden for particles from distant galaxies. These outliers are the heart of the mystery. So what could be accelerating these rule-breaking particles? The prime suspects are the most violent and energetic engines in the universe. At the top of the list are active galactic nuclei, where supermassive black holes, billions of times the mass of our Sun, devour matter and funnel unimaginable energy into colossal jets of plasma that can stretch for millions of light years. These jets could act as natural particle accelerators on a godlike scale. Other potential sources include gamma-ray bursts, the explosive deaths of massive stars that for a brief moment outshine an entire galaxy, or the violent mergers of ultra-dense objects like neutron stars. Some theorists have proposed even more exotic origins, such as defects in the very fabric of space-time, left over from the Big Bang, known as cosmic strings, vibrating and releasing immense bursts of energy. The quest to definitively identify the source is a monumental challenge because these particles are charged. Unlike photons of light that travel in straight lines, protons and atomic nuclei are pushed and pulled by the interstellar and intergalactic magnetic fields that fill the cosmos. Their paths are scrambled and bent, making it nearly impossible to trace a single particle back to its origin in a straight line. It's like trying to find the source of a river by following a single leaf that has been tossed and turned by countless currents along the way. To overcome this, scientists must employ statistical methods, looking for clusters of these ultra-high-energy events on the sky map and checking if they align with known celestial landmarks. Intriguingly, the Telescope Array experiment recently reported a hotspot, a region of the sky near the constellation Ursa Major that appears to have an overabundance of these extreme energy events. While not yet a definitive identification, this hotspot provides a tantalizing clue, a potential cosmic hunting ground where we might finally find the engines capable of launching the universe's most energetic particles. Each detection that breaches the GZK limit is more than just a data point. It is a challenge to our understanding, a piece of a puzzle that could ultimately force us to rewrite the textbooks on particle physics and astrophysics. The Hubble tension is far more than a minor statistical discrepancy. It is a growing crack in the foundation of modern cosmology, and the latest data has only widened the divide. On one side, the SH0ES team, led by Nobel laureate Adam Rees, continues to refine the cosmic distance ladder with painstaking precision. Their most recent observations, leveraging the razor-sharp vision of the James Webb Space Telescope, were designed to eliminate the last major source of uncertainty, potential errors in the measurement of Cepheid variables in galaxies that are host to Type 1a supernova. The brilliant hope was that Webb's ability to see straight through the obscuring cosmic dust would finally bring the two measurements into alignment. Instead, the opposite happened. The new data confirmed the SH0ES measurement with even greater confidence, solidifying a Hubble constant value of roughly 73 kilometers per second per megaparsec. This means that for every million parsecs of distance, a galaxy is receding 73 kilometers per second faster. The local universe is expanding at a rate that our standard model struggles to accept. On the other side, the Planck collaboration's measurement, derived from the exquisite map of the cosmic microwave background, remains firmly anchored at 67.4. This value isn't a direct observation of today's expansion, it's a prediction. Planck's data gives us a snapshot of the infant universe, and when we feed that snapshot into our remarkably successful lambda CDM model, which includes dark matter, dark energy, and the known laws of physics, it tells us exactly how fast the universe should be expanding today. The fact that these two gold standard measurements, each backed by a different Nobel Prize, refuse to converge suggests that the problem may not be with our measurements, but with the model itself. The model is the recipe for the entire cosmos, and if it predicts an expansion rate that doesn't match what we see, then perhaps an ingredient is missing or we've misunderstood the measurements of the ones we have. This has led cosmologists to propose a suite of extraordinary solutions, each one more fascinating than the last. One of the most compelling ideas is known as early dark energy. This theory posits that a new, previously unknown form of dark energy existed for a brief moment in the very early universe, just before the release of the cosmic microwave background. This transient energy field would have added an extra dose of repulsion during that critical period, subtly changing how sound waves propagated through the primordial plasma. This would affect the pattern of hot and cold spots we see in the CMB. To match the Planck data, the model would then require a slower expansion rate today. It's a tiny, early adjustment that ripples forward billions of years to resolve the tension. The catch is that this early dark energy must have been active for only a short time and then vanished without a trace, leaving us to wonder what could cause such a fleeting yet profound influence. Other theorists are looking not to new ingredients but to a modification of the most fundamental force, gravity itself. Models of modified gravity, such as those that suggest the strength of gravity, may have been different in the past or may vary on cosmic scales, offer another pathway. If gravity was slightly weaker in the early universe, it would have taken longer for the large-scale structures we see to form. This would also nudge the predicted Hubble constant from the CMB to a higher value, potentially bringing it closer to the local measurement. Yet, tampering with Einstein's theory of general relativity is a monumental step, as it has passed every other test with flying colors for over a century. Any modification must be incredibly subtle, fixing the Hubble problem without breaking everything else we know about how gravity works with planets, stars, and black holes. The path to a resolution lies in a new generation of observatories that will peer deeper into the cosmos than ever before. The Vera C. Rubin Observatory, with its unprecedented sky survey, will discover thousands more supernovae, building a vastly more detailed map of the expansion history. The Nancy Grace Roman Space Telescope will hunt for the most distant Type 1, a supernova, and study the distribution of galaxies with incredible precision. Perhaps most crucially, scientists are turning to entirely independent methods to break the tie. One such method involves studying the faint echoes of sound waves frozen into the distribution of galaxies, a fossil record known as baryon acoustic oscillations. Another uses the light from bright quasars as it passes through the filamentary web of intergalactic hydrogen, a technique called the Lyman alpha forest. These independent probes are beginning to return their own values for the Hubble constant, and intriguingly, some are landing in the no man's land between the SH0 ES and Planck values, adding a new layer of intrigue to the mystery. The Hubble tension is no longer a quiet debate in the back rooms of astronomy conferences. It is a frontline battle for the soul of cosmology. With each passing year, as the measurements become more precise and the discrepancy more stubborn, the excitement grows. Cosmologists know they are on the verge of something profound. They are not merely arguing over numbers on a chart. They are grappling with the possibility that the universe is trying to tell us something we haven't yet learned how to hear. We may be standing at the precipice of a revolution, one that will reveal a deeper, richer tapestry of physical law than we ever imagined. But just as we grapple with large-scale alignments and cosmic flows, another anomaly in the ancient light of the cosmos demands our attention. A chill in the afterglow of creation so pronounced it might be a window into something truly exotic. This is the mystery of the CMB cold spot, a vast and perplexingly cold region in the cosmic microwave background that has sparked a decades-long debate between two equally incredible explanations. Imagine looking at a full sky map of the faint heat left over from the Big Bang. It's a tapestry of tiny temperature variations, hot and cold spots that represent the seeds of all future structure. Most of these fluctuations are incredibly small, differing from the average temperature by mere millionths of a degree. But one spot located in the constellation Eridanus stands out like a cold sore on the face of the universe. It's a massive region spanning over 1.8 billion light-years across, where the temperature is about 70 microkelvin colder than the surrounding average. That may not sound like much, but statistically, a spot this large and this cold is a profound outlier. In a universe that is supposed to be largely random and Gaussian in its fluctuations, the cold spot is a 5 sigma event, something that should be so incredibly rare that its very existence makes us question whether our models of the cosmos are complete. So what could cause such a deep freeze in the primordial sky? The leading and more conservative explanation is the integrated Sachs-Wolf effect, amplified by a truly colossal cosmic void. The integrated Sachs-Wolf effect is a subtle phenomenon that occurs when light travels through an evolving gravitational landscape. As a photon from the CMB enters a region of space that is underdense, a void it must climb out of a gravitational well. In a universe dominated by matter, the well would deepen as the photon traverses it, and the energy lost climbing out would be regained. But in a universe with dark energy, the expansion is accelerating, causing the gravitational potential of the void to actually become shallower while the photon is inside it. The photon climbs out of a well that is not as deep as when it entered, and it therefore retains a tiny bit of extra energy, appearing slightly blue-shifted or hotter. However, this is the opposite of what we see with the cold spot. The counterintuitive part is this: if a void is extremely large and evolving very quickly due to dark energy, the effect can sometimes work in reverse in a way that actually loses energy, making the CMB light passing through it appear colder. This is the supervoid hypothesis. The idea is that between us and the cold spot lies a gargantuan underdensity of matter, a supervoid so immense that its gravitational influence combined with dark energy imprints this cold signature on the light that passes through it. The hunt for this proposed supervoid has been a major astronomical effort. By meticulously mapping the distribution of galaxies in the direction of the cold spot using large redshift surveys, astronomers have indeed found evidence of a significant underdensity. This proposed void, often called the Eridanus supervoid, is estimated to be enormous, perhaps 500 million to 1 billion light-years wide. The correlation between its position and the cold spot is tantalizing. However, the plot thickens because many sophisticated computer simulations suggest that even a void of this staggering size may not be sufficient to explain the full depth of the coldness we observe. The numbers just don't quite add up. The predicted cooling from the supervoid seems to be too weak to account for the extreme temperature dip. This discrepancy has led some scientists to propose a far more radical and thrilling alternative. Perhaps the cold spot is not a sign of a lack of something, but the signature of a cosmic crash, a collision with another universe. This idea falls under the umbrella of cosmic textures, which are exotic defects in the fabric of space-time, theoretical knots or wrinkles that could have formed during a phase transition in the very early universe. If one of these textures exists, it would create a gravitational potential well so unusual that any CMB photon passing through it would lose a significant amount of energy, emerging much colder. This would leave a distinct circular cold spot in the sky, exactly like the one we see. Even more speculatively, some theories suggest such a texture could be a bruise left on our universe from a colossal impact with a bubble of another universe in the vast multiverse. It's a concept that stretches the imagination to its breaking point, suggesting that the cold spot could be our first empirical evidence for a reality beyond our own. The debate between the supervoid and the exotic physics explanation is far from settled. New, more detailed galaxy surveys are continuously refining our map of the large-scale structure in that direction, trying to pin down the true size and emptiness of the proposed void. At the same time, cosmologists are running ever more complex simulations to see if a combination of a void and other known factors could, against the odds, produce the anomaly. The cold spot remains one of the most tantalizing puzzles in cosmology because it forces us to confront the limits of our understanding. It is either a testament to the strange and amplified effects of dark energy and cosmic voids, acting in a way we don't fully grasp, or it is something far more profound, a flaw in the smooth fabric of our universe, a scar from a primordial event that could open a door to physics we have yet to dream of. But just as we map the grand flows of galaxies toward the great attractor and away from the dipole repeller, an even more profound and controversial motion has been proposed, a mysterious, coordinated drift on a scale so vast it seems to defy the very notion of a finite cosmos. This enigma is known as dark flow, and it suggests that hundreds of millions of light-years from Earth, entire clusters of galaxies are moving in a collective stream, pulled by a gravitational force so immense that its source must lie beyond the edge of everything we can see. The story of dark flow begins with a subtle and brilliant technique for measuring the motion of the most massive structures in the universe, galaxy clusters. These clusters are not empty, they are filled with a hot, thin plasma of ionized gas. When the ancient light from the cosmic microwave background passes through this seething cloud, it interacts with the energetic electrons within it. This interaction, known as the Sunyaev-Zeldovich effect, imparts a tiny but measurable boost in energy to the CMB photons. Normally, this effect is used to map the location and mass of these clusters. However, if the cluster itself is moving at a high velocity relative to the rest frame of the CMB, it creates a secondary, kinetic version of this effect. The motion of the hot gas causes a slight distortion in the CMB's spectrum in that specific direction, a minute Doppler shift that acts like a cosmic speed gun. By carefully analyzing this kinetic Sunyaev-Zeldovich effect across hundreds of distant clusters, astronomers can theoretically detect their bulk motion through space. A team led by astronomer Alexander Kashlinsky applied this method to a huge catalog of galaxy clusters, using data from the Wilkinson microwave anisotropy probe and later the Planck satellite. Their results were staggering. They found evidence that these clusters were not moving randomly. Instead, they reported a consistent, coherent flow, a dark flow, of hundreds of kilometers per second, all in the same general direction, roughly toward the constellations Centaurus and Vela. This wasn't just a few rogue clusters, it was a statistical trend across a vast volume of space, seemingly indicating a coordinated motion for structures billions of light-years away. The most shocking implication was that the gravitational pull causing this motion would have to originate from a source so far away that its light has not had time to reach us in the entire history of the universe. We are, in effect, seeing the gravitational shadow of something entirely outside our observable horizon. Naturally, a claim this extraordinary has been met with intense scrutiny and skepticism from the wider cosmological community. The primary challenge is that the kinetic SZ effect signal is incredibly faint, buried deep within a sea of noise from the CMB itself and other foreground emissions. Detecting it requires meticulous statistical analysis and careful subtraction of all other possible contaminants. Several independent teams have attempted to replicate the findings using different methodologies and data sets with mixed results. Some analyses have failed to find any significant evidence for a dark flow, suggesting the original signal might be a systematic artifact, perhaps an unaccounted-for glow from within our own solar system or an error in the cluster catalog itself. The Planck satellite team, with its superior data, conducted its own search and found hints of a bulk flow, but at a much smaller amplitude and scale than originally claimed, which could potentially be explained by the known gravitational pull of nearby superstructures like the Shapley supercluster. The debate continues, a high-stakes game of cosmic chess played with the most precise data we can gather. If dark flow is real, its implications are nothing short of revolutionary. It would suggest that the enormous mass concentrations beyond our observable universe are exerting a gravitational influence on us, providing the first indirect evidence for a cosmos that is far larger and stranger than we ever imagined, perhaps even infinite and containing regions with vastly different properties from our own. It would mean our universe is not an isolated island but part of a much grander structure, a multiverse where our observable domain is just one bubble in a frothing sea of creation. If it is not real, its investigation still represents a triumph of scientific audacity, pushing our methods to their absolute limits in the quest to understand our place in the totality of existence. The mystery of dark flow forces us to look at the edge of our map and wonder what uncharted territories, what unimaginable giants might lie just beyond the light. From the vast, mysterious flows of dark matter to the subtle chill of the CMB cold spot, we've explored cosmic puzzles on the grandest scales. But now, let's turn our gaze to a mystery that is simultaneously astronomical and deeply intimate: one that connects the void between the stars to the very essence of our own existence. How did the fundamental building blocks of life, the organic molecules necessary for biology, come to be, and could they have formed in the cold, empty vacuum of space itself? For a long time, the prevailing assumption was that the space between stars was just that empty space, a void where simple atoms like hydrogen and helium drifted in isolation. The idea that this environment could be a factory for the complex chemistry required for life seemed absurd. How could carbon-based molecules with their intricate structures possibly assemble in such a frigid, radiation-bathed nothingness? The answer began to reveal itself not through telescopes initially, but from rocks falling from the sky. Meteorites, particularly a type known as carbonaceous chondrites, have been delivering clues for centuries. When scientists painstakingly analyzed the composition of these ancient space rocks, like the famous Murchison meteorite that fell in Australia in 1969, they made a staggering discovery. These meteorites were not just simple stone, they were loaded with a rich variety of organic compounds. They contained amino acids, the very molecules that string together to form proteins, which are the workhorses of all known life forms. But it wasn't just a few familiar types. The Murchison meteorite was found to contain over 90 different amino acids, most of which are never used in earthly biology. This was a clear sign that nature was conducting chemistry on an industrial scale out in the cosmos, creating a vast library of organic molecules long before our solar system even formed. So how does this happen? How do you go from atoms to amino acids in the deep freeze of an interstellar cloud? The process is surprisingly elegant and occurs in the vast molecular clouds that drift through our galaxy, the same nurseries where stars and planets are born. These clouds are not completely empty. They are filled with tiny grains of silicate dust and carbon, finer than smoke. On the cold surfaces of these dust grains, single atoms and simple molecules like carbon monoxide, ammonia, and water slowly stick, forming a thin layer of frost. This icy mantle becomes a tiny chemical laboratory. The environment is bathed in cosmic radiation, which can break apart molecules, creating highly reactive fragments known as radicals. These radicals, trapped together on the dust grain, don't need the heat we traditionally associate with chemical reactions. In the extreme cold, they can slowly tunnel through energy barriers and eventually link up to form more complex molecules. Then, when a newborn star ignites nearby, its warmth gently heats the ices, releasing these newly formed organic compounds into the surrounding gas. This is where radio astronomy comes in. Giant dishes like the Atacama Large Millimeter Array can tune into the specific radio frequencies that these molecules emit as they tumble through space. Astronomers have now identified a menagerie of complex organics in these clouds, from simple sugars like glycolaldehyde to precursors to amino acids and even ethanol alcohol. It appears the universe is not just capable of making the ingredients for life, it's doing it everywhere all the time. This discovery naturally leads to a profound and controversial hypothesis, panspermia. If the raw materials of life are ubiquitous throughout the galaxy, is it possible that life itself, or at least its crucial components, could hitch a ride from one world to another? The idea of panspermia suggests that life on Earth may not have originated here independently. Instead, it could have been seeded by comets or asteroids delivering a payload of pre-formed organic molecules, or even extremophile microbes capable of surviving the long journey through space. While the notion of fully fledged life making an interstellar trip faces immense hurdles, namely radiation and timescales, the delivery of complex organics is virtually certain. We know that in the early history of our solar system, a period known as the Late Heavy Bombardment, Earth was relentlessly pummeled by comets and asteroids. These objects formed from the very same organic rich molecular cloud that gave birth to our Sun, would have carpet-bombed our planet with amino acids, sugars, and other critical compounds. This delivery service could have provided the essential starter kit, significantly enriching the probiotic soup of the early Earth and dramatically increasing the chances that life would emerge. This cosmic perspective completely reframes a landmark experiment from the 1950s, the Miller-Urey experiment. Stanley Miller and Harold Urey famously simulated the conditions of early Earth in a glass apparatus, combining water, methane, ammonia, and hydrogen gases they believed made up the primordial atmosphere, and zapping it with electrical sparks to simulate lightning. Within days, the flask turned cloudy and then a deep red, and analysis revealed it was teeming with amino acids. For decades, this was hailed as proof that the building blocks of life could easily form on a young planet. But what if we've been looking at it backwards? The Miller-Urey experiment didn't just simulate a hypothetical earthly atmosphere. It inadvertently recreated the conditions of interstellar ice grains being warmed by a young sun. The ingredients they used are the very same molecules we now know are abundant in molecular clouds and comets. Their groundbreaking work may have been less about how life could have started on Earth, and more a demonstration of the universal chemical processes that were already happening across the galaxy for billions of years, processes that ultimately stocked the pantry of our solar system with the ingredients for life before Earth was even finished forming. This shifts the origin story from a uniquely planetary event to a truly cosmic phenomenon, suggesting that the universe may be inherently bio-friendly, perpetually weaving the threads of chemistry that can, under the right conditions, be knitted into the tapestry of life. And after considering all these cosmic mysteries, from the building blocks of life scattered between the stars to the vast, unexplained flows of distant galaxies, we arrive at perhaps the most haunting question of all, one that touches our very place in the cosmos. If the universe is so vast and so old, and the ingredients for life seem to be everywhere, then where is everybody? This simple, profound question, famously posed by physicist Enrico Fermi over a lunchtime conversation, has become known as the Fermi Paradox. It highlights the startling contradiction between the high probability of extraterrestrial civilizations and the complete lack of any observable evidence for them. Our galaxy, the Milky Way, is around 13.6 billion years old and contains an estimated 100 to 400 billion stars. A significant fraction of those stars are orbited by planets in the habitable zone, where temperatures could allow for liquid water. Even if the odds of life arising on any given planet are astronomically small, the sheer number of opportunities suggests the galaxy should be teeming with life. And if even a tiny fraction of that life becomes intelligent and technological, it should have had more than enough time to spread across every corner of the Milky Way. The silence we hear is, therefore, deeply unsettling. This is where the concept of the Great Filter enters the picture, a hypothetical stage in the evolution of life that is extremely difficult to overcome. The idea is that somewhere on the path from non-living matter to a spacefaring civilization that endures for millions of years, there is a barrier, a filter, that prevents almost everyone from making it to the other side. The terrifying implication of this theory is its location. If the Great Filter is behind us, if it was a step that we on Earth have already miraculously passed, then we might truly be alone, the first and only civilization to have made it this far in our galaxy. This filter could have been the near-miraculous origin of life itself from non-living chemistry, or perhaps the leap from simple prokaryotic cells to complex eukaryotic cells, an evolutionary transition that took well over 1 billion years on Earth and might be exceedingly rare elsewhere. The far more frightening possibility is that the Great Filter still lies ahead of us. This is the hypothesis that the development of a technological civilization inevitably leads to its own destruction before it can successfully colonize other stars. There are several grim candidates for this future filter. It could be the existential risk of nuclear annihilation, a war from which no civilization recovers. It could be the unleashing of a genetically engineered pathogen, a pandemic with a 100% fatality rate. It could be the unforeseen catastrophe of a physics experiment that goes horribly wrong, or the rise of a superintelligent artificial intelligence that sees its creators as an obstacle to its goals. Or it could be a more subtle failure, a societal collapse driven by the unsustainable consumption of a planet's resources, leading to an irreversible ecological breakdown that strands a species on its home world forever. If this is the case, then the eerie silence of the cosmos is a graveyard warning, a sign that no one makes it through this technological adolescence. Every civilization that reaches our level of advancement ultimately creates the tools of its own destruction, and we may be naively walking down that very same path. Of course, there are less ominous solutions to the paradox. Perhaps intelligent life is common, but it chooses not to announce its presence. This is the zoo hypothesis or the planetarium hypothesis, which suggests that Earth is intentionally isolated, placed in a kind of cosmic quarantine or wildlife preserve by a vastly older and more advanced civilization. They might be observing us from a distance, waiting for us to reach a certain level of maturity or technological wisdom before making contact, much like the prime directive in science fiction. Another idea is that space is simply too big and the timescales too vast. Civilizations might bloom and fade like fireflies in the night, their lifespan so short compared to the distances between stars that they never overlap in a way that allows for communication or contact. Or maybe the modes of communication are so advanced and alien that we simply don't know how to listen. Their signals could be embedded in the fabric of spacetime itself, or use technologies we haven't even dreamed of, making them completely undetectable to our primitive radio telescopes. The true weight of the Fermi Paradox isn't just an intellectual exercise, it's a mirror held up to humanity. It forces us to confront our own future and the choices we are making right now. Are we destined to be just another brief, bright flash in the cosmic dark? A civilization that briefly wondered about the stars only to vanish without a trace? Or will we navigate the challenges of technology, climate, and our own tribal instincts to become a stable, multi-planetary species, effectively passing through the great filter and ensuring our survival for millennia to come? The paradox offers no answers, only a profound responsibility. The silence from the stars is not an empty void to be feared, but a challenge to be met. It is a dare for us to grow up, to become the ancient, wise civilization we hope to find, and to finally break the silence ourselves by ensuring our light continues to shine in the cosmic night. After confronting the profound silence of the cosmos, we turn inward to a mystery that underpins our very experience of reality, the nature of time itself. We all feel its relentless, one-way flow, the fact that we remember the past but not the future, that eggs scramble easily but never unscramble themselves. This directionality, this arrow of time, is so fundamental to our existence that we rarely stop to question it. Yet, according to the fundamental laws of physics, this is the deepest puzzle in the universe. The microscopic laws that govern particles, like those in quantum mechanics, are almost entirely time-symmetric. They work just as well if time runs forward or backward. So why does the macroscopic universe we live in have such a powerful and obvious direction? The answer, surprisingly, is written in the very first moment of creation. The key to this puzzle is a concept called entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It's this statistical tendency toward disorder that gives us the arrow of time. Milk mixes into coffee, ice cubes melt in a warm drink, and perfume disperses throughout a room. All of these are examples of entropy increasing. But here's the cosmic shock. For entropy to increase, it had to start from an incredibly low value. The universe must have begun in a state of exceptionally low entropy, a state of exquisite and improbable order. Think of it like a deck of cards fresh from the factory, perfectly arranged by suit and number. From that ordered state, it's easy to shuffle it into disorder, but it's virtually impossible to randomly shuffle a disordered deck back into that pristine factory order state. The Big Bang was that factory-sealed deck. The primordial universe was an incredibly hot, dense, and, this is the crucial part, smoothly uniform soup of energy. This might not sound ordered, but in gravitational terms, it was a state of incredibly low entropy. A perfectly smooth distribution is highly ordered. It has nowhere to go but toward the clumpiness of galaxies, stars, and planets, which are actually states of much higher entropy when gravity is taken into account. This presents perhaps the most profound why question in all of science. Why did the universe begin in such a special, low-entropy state? This isn't a question about the mechanism of the Big Bang, but about the initial conditions themselves. The laws of physics can tell us how the universe evolved from that point, but they cannot tell us why it started there. It's a staggering fine-tuning problem. If any of a near-infinite number of possible starting conditions had been chosen, the universe would have been stillborn, a chaotic, high-entropy mess from the outset, with no arrow of time, no formation of structures, and certainly no one around to ponder the question. Our existence hinges on this impossibly unlikely starting point. This mystery forces physicists to consider radical possibilities. One compelling idea is that our universe is just one bubble in a vast multiverse. In this eternal inflationary landscape, countless universes are constantly popping into existence, each with its own random set of physical laws and initial conditions. The vast, overwhelming majority of these universes would have high initial entropy and be devoid of life or structure. We, of course, find ourselves in one of the rare, finely tuned universes that permits complexity and consciousness. Our low entropy beginning isn't a miracle, it's a selection effect. We are here because this is one of the few places where beings like us could ever exist. This line of thinking dovetails with an even more revolutionary idea, that time itself may not be a fundamental property of the universe. In our quest for a theory of everything, particularly in approaches like loop quantum gravity or string theory, many physicists find that time seems to vanish from the core equations at the most fundamental level. This suggests that time, as we experience it, might be an emergent property, a kind of illusion that arises from the collective behavior of something more basic. It could be a thermodynamic phenomenon, a byproduct of the increase in entropy, or in the holographic principle, time might emerge from a more fundamental, timeless description encoded on a boundary of the universe. Perhaps the flow of time is related to the quantum entanglement of particles. Each of these theories paints a picture where our visceral experience of past, present, and future is a compelling story our brains tell us about a deeper, more complex reality that exists all at once. The implications are enough to make your head spin. If time is not fundamental, then the distinction between past, present, and future may be a persistent illusion, as Einstein once suggested. The universe might be a static, four-dimensional block where every event in history exists eternally in its designated place. Our conscious awareness would then be like a spotlight moving along this block, creating the subjective feeling of a flowing now. This doesn't make our experience any less real, but it suggests that the true nature of reality is far stranger and more magnificent than our everyday perception allows us to see. Solving the mystery of time's arrow and its origin is more than an academic exercise. It is a journey to understand why we have a past to learn from and a future to look forward to it all. Yet this growing discrepancy is far more than a simple measurement error. It is a powerful beacon illuminating the potential limits of our standard cosmic model, lambda CDM, and pointing toward thrilling new physics. Lambda CDM has been the reigning champion of cosmology for decades, a robust framework built upon the pillars of a cosmological constant, lambda representing dark energy and cold dark matter. It has beautifully explained the large-scale structure of the universe, the precise patterns in the cosmic microwave background, and the abundance of light elements. But the stubborn refusal of the Hubble constant measurements to converge suggests that this model, for all its success, might be incomplete. It's as if we've been using a brilliantly accurate map that suddenly fails to account for a newly discovered continent. We need to add new details to the chart. This has propelled cosmologists to explore radical alternatives that tweak or even overhaul components of the standard model. One of the most compelling ideas is that of interacting dark energy. In lambda CDM, dark energy is a constant, passive force inherent to the vacuum of space. But what if it's dynamic? What if it evolves over time and, crucially, interacts with dark matter? In these models, dark energy could be slowly decaying into dark matter, or perhaps dark matter is converting into dark energy. This energy exchange would subtly alter the expansion history of the universe. The early universe would evolve differently, changing the sound horizon scale imprinted on the CMB, and thus the predicted value for the Hubble constant today. By allowing this interaction, theorists can nudge the CMB prediction upward, potentially closing the gap with the local distance ladder measurements. It's an elegant solution that retains the core of the standard model, while introducing a new, dynamic relationship between its two most mysterious components. Another profound possibility is that the fundamental constants of nature are not so constant after all. What if the force of gravity, or the mass of the electron, or the fine structure constant were slightly different in the early universe? The idea of varying constants is not new, but the Hubble tension gives it renewed urgency. If, for example, the strength of gravity was weaker in the first few 100,000 years after the Big Bang, the growth of cosmic structures would have been slightly delayed. This would modify the interpretation of the CMB patterns, leading to a higher predicted value for the present-day expansion rate. These models are incredibly subtle, as any variation must be tiny enough to have escaped detection in laboratory experiments and observations of other astrophysical phenomena, yet significant enough to resolve a 5% discrepancy in the Hubble constant. It's a tightrope walk for theorists, but the potential payoff is a revolutionary understanding of the laws of physics. The race to solve this tension is driving the development of a new generation of astronomical observatories, each designed to measure the cosmic expansion with unprecedented precision and through independent methods. The Vera C. Rubin Observatory, with its massive mirror and enormous camera, will conduct a decade-long survey of the sky, discovering tens of thousands of new supernovae and meticulously mapping the distribution of galaxies to measure baryon acoustic oscillations. This will provide a completely new, high-precision measurement of the expansion history, independent of both the distance ladder and the CMB. Similarly, the Nancy Grace Roman Space Telescope will peer into the infrared, hunting for the most distant Type 1a supernova and studying the light of galaxies at cosmic noon with a clarity we've never had before. Perhaps the most crucial independent test comes from studying the cosmic distance ladder's very first rung. The Gaia satellite is currently conducting a census of over 1 billion stars in our galaxy, measuring their positions and distances with extraordinary accuracy through parallax. This data is refining our understanding of Cepheid variables and the geometry of our local cosmic neighborhood, tightening the calibration of the entire distance ladder from its foundation. At the other end of the spectrum, detailed studies of the gravitational lensing of distant quasars by foreground galaxies provide yet another cosmic ruler, one that is sensitive to the geometry of the universe and entirely independent of the other techniques. As these missions deliver their torrent of new data over the coming years, we will be presented with a clear choice. The tension will either resolve itself, revealing a subtle systematic error we had overlooked, or it will sharpen into an undeniable crack in our foundational model. Either outcome is a victory for science. One gives us greater confidence in our current understanding, while the other flings open a door to a new, deeper, and undoubtedly more strange cosmology. The Hubble tension is not a crisis to be feared, but a conversation the universe is having with us, a cryptic clue that we are on the verge of translating, one that promises to reveal whether our map of the cosmos needs a minor adjustment or a complete and glorious redrawing. But this grand cosmic forecast of heat death or a big rip leads us to the final, and perhaps most personal, mystery on our list. What is the ultimate fate of information, and with it, consciousness itself? If the universe is destined for a cold, dark, and empty future, does anything we've ever thought, done, or been truly matter in any lasting sense? Or could some echo of experience persist, encoded in the fabric of reality long after the last star has died? This question pushes us to the very boundaries of physics and philosophy, where science bleeds into profound speculation about the nature of existence. At the heart of this is the concept of quantum immortality, a thought experiment that emerges from the many worlds interpretation of quantum mechanics. In this view, every time a quantum event occurs with multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. Now apply this to a conscious observer. Imagine a hypothetical experiment where your survival depends on a random quantum event, like the decay of a radioactive atom. In the branch where the atom decays, you die, but from your subjective perspective, you can only ever experience the branches where you continue to be alive. You would find yourself miraculously surviving every single time, no matter how improbable. While this isn't a literal recipe for living forever, aging would still involve countless quantum events where you die in most branches. It raises a bizarre possibility. The subjective stream of consciousness might always find a way to continue in some branch of the multiverse indefinitely. It suggests that from a first-person perspective, consciousness might never experience its own end, always following a timeline where it persists against all odds. This is, of course, a deeply controversial and unsettling idea, less a theory and more a logical paradox that highlights the strange implications of how we interpret quantum theory when applied to the self. A less mind-bending but equally grand concept is cosmological natural selection, proposed by physicist Lee Smolin. This theory applies the principle of Darwinian evolution to the cosmos itself. The idea is that universes can reprogate through the formation of black holes, which Smolin suggests could spawn new, baby universes inside their singularities. Each new universe would inherit its fundamental physical constants, the strength of gravity, the mass of an electron, with slight random variations, much like genetic mutations. Universes that are more efficient at producing black holes would, by this process, create more offspring universes. Over countless generations, this would lead to the evolution of universes fine-tuned for black hole production. The fascinating implication here is not for our individual consciousness, but for the persistence of information and structure across cosmic generations. The laws of physics in our universe, which allow for the existence of stars, planets, and life, might not be a miraculous accident, but simply the result of a blind evolutionary process that favors black hole fertility. In this view, while our specific universe will die, the information that defines its laws, the very framework that allows complexity and perhaps consciousness to arise, is passed on and refined in an endless cycle of cosmic birth and death. Yet, even if our lineage of universes continues forever, the fate of any specific thought, memory, or feeling within our own cosmos seems grim based on known physics. As the universe accelerates toward its heat death, all energy gradients will eventually even out. Without a difference in energy, no work can be done and no information can be processed. It will be a state of maximum entropy, a cosmic equilibrium where nothing happens and nothing ever will again. In this final state, is any information truly lost? The laws of quantum mechanics suggest that information cannot be destroyed, but it can be rendered utterly irretrievable and meaningless. It would be like writing a beautiful poem in the arrangement of molecules in a drop of ink, and then dropping that ink into the ocean and waiting for it to perfectly diffuse throughout the entire Earth's waters. The information of the poem still exists in the precise position of every atom, but it is scrambled and diluted across such a vast volume that it is functionally lost forever. This would be the fate of all information in the universe, from the genetic code of the first life forms to the data of every computer that will ever be built, preserved in principle, but inaccessible and inert for all eternity. This leads us to the final philosophical question: what is the relationship between consciousness and this cosmic scale information processing? Some theories of consciousness, like integrated information theory, propose that consciousness is a form of integrated information. If that's true, then as the universe evolves toward a state where information can no longer be integrated or processed, where no complex structures can form, then consciousness itself must inevitably fade from the cosmos. The universe would not only become lifeless but also mindless, a void without a single point of awareness to witness its immense, silent conclusion. The ultimate fate of consciousness, then, might be a return to the oblivion that preceded the Big Bang. Yet, the sheer fact that we are here now, in a universe capable of generating beings that can contemplate their own origins and end, is itself a staggering wonder. Our brief flicker of awareness against the unimaginable vastness of space and time becomes its own kind of answer. We are the universe's way of knowing itself, and even if that knowledge is temporary, its existence is a profound and beautiful feature of cosmic history. The story of the universe may ultimately be a story without a permanent reader, but for a time there were chapters filled with wonder, curiosity, and the brilliant, fragile light of conscious thought. And so, our journey through 25 of the universe's greatest enigmas brings us not to an end but to a new beginning, a starting point for wonder. From the ghostly pull of dark matter and the relentless push of dark energy, to the fleeting brilliance of fast radio bursts and the haunting silence of the Fermi Paradox, each mystery we've explored is a testament to a cosmos that is far stranger, more dynamic, and more magnificent than we could have ever imagined. We've seen how the universe's very first moments are still imprinted in the lithium deficit and the cold spot on the ancient sky, and how its final fate is written in the enigmatic equation of state of the very vacuum of space. We've pondered the nature of time, the fabric of reality, and the profound possibility that our entire existence might be a holographic projection from the edge of a black hole. These puzzles are not mere gaps in our knowledge, they are the very engines of scientific discovery. Each one is a compass pointing toward a new horizon of understanding, a challenge that has inspired generations of astronomers, physicists, and dreamers to build bigger telescopes, devise more elegant theories, and peer deeper into the unknown. The history of science tells us that our most profound breakthroughs often come not from having all the answers, but from learning how to ask better questions. The discomfort of not knowing, the tension of a paradox, the frustration of a measurement that refuses to conform, these are the moments that force us to rethink our assumptions and venture into uncharted intellectual territory. The Hubble tension isn't a crisis, it's an invitation. The black hole information paradox isn't a dead end, it's a doorway. These mysteries are the universe's way of teaching us, of guiding us toward a richer, more complete story of where we came from and what we are a part of. There is a profound beauty in the unanswered question. It keeps our curiosity alive, fueling a sense of awe that is as essential to the human spirit as knowledge itself. To look up at a starry night and be filled with questions is to participate in a tradition that connects us to every human who has ever gazed heavenward, from the first storytellers who saw myths in the constellations to the scientists who see the fingerprints of the Big Bang in the static between channels. This quest for understanding is what we are made for. It is a celebration of our desire to explore, to learn, and to find our place in the grand cosmic scheme. Now, we'd love to hear from you. Which of these 25 mysteries captured your imagination the most? Was it the terrifying potential of the Big Rip, the eerie coordination of the aligned quasars, or the cosmic detective story of the missing baryons? Let us know your favorite in the comments below. We read every single one. And if you want to keep exploring the wonders of the cosmos with us, make sure to hit that subscribe button and ring the notification bell. We're just getting started on our journey through the universe's deepest secrets, and we can't wait to have you along for the next chapter. Thank you for watching and never stop looking.